The purpose of this video is to establish a way of thinking about the derivative of a composite function. And the way we're going to do it is first review about the idea of derivative. Specifically, we're going to focus on just estimating the change in an output of a function relative to changes in its input. And then we're going to extend that idea to a composite function. How would that idea work if we had a composition of two functions? And so here's how it starts. So I'm going to draw here just a function. Now remember, when we do calculus, we're really looking at instantaneous rates of change. That is the average rate of change over a really small space. And when we zoom in on a really small space, what we're going to see is just what appears to be linear function. So even though I'm showing something relatively straight here, know that I've just zoomed in so much that the curvy graph looks linear at this point. So here's how the idea of derivative, or how estimating how a function changes relative to changes in its input. We're going to review how that looked in just a regular function. So for some input value a, we get an output value of f of a. Now, what happens in calculus is we change that input quantity by some amount called delta x. Now, we know that that change in delta x, or that change in x, is going to be something really small. For the sake of this, I'm zoomed in so far that this change in x appears to be relatively big. So we're going to change x by delta x. So where x was measured at a, we're now going to increase it by delta x. So then we're going to output a quantity called f of a plus delta x. All right, now when we measure that rate of change, what we're really kind of focused in on is that change in x produces a corresponding change in f of x, and it's that change in f that we're most interested in. So just visually, I hope you can see f of a is this vertical length right here, and f of a plus delta x is this vertical length right here. And so this delta f is the difference between f of a plus delta x and f of a. That is, delta f is that vertical length f of a plus delta x minus f of a. Now, another way to think about this is to remind ourselves of the limit definition of derivative. So hopefully this is just a reminder that looks familiar. As delta x approaches 0, that ratio of the difference in the output quantities relative to changes in the input is what we call the derivative, and we notate it as f prime of a. Notice that we kind of almost have it. Well, we have the numerator of that here. And so the numerator of that is here. Can you imagine if we multiplied by delta x, that numerator, at least in terms of an estimation, since we're not taking the limit, is f prime of a times delta x. So coming over here, multiplying by delta x, f prime of a times delta x would be just that numerator, ignoring the limit because we're just estimating the change in the output, not allowing delta x to go to 0 at this moment. And so there you go. That change in f could be expressed by saying f prime of a times delta x. Now watch this. We're going to examine the same way of thinking, but not on a function f of x, but on the composition of two functions. There's another function, g, that is the composition with f of x. And so keep in mind that with composition of functions, it was the output in one function becomes the input in the next. And so instead of inputting an a, we're now going to input an f of a. So I'm going to be as careful as I can, but just to kind of match up here, f of a is this length right here. So then f of a is going to be that same length down here. Also, just pretend that same thing. We're zooming in on a particular function, and we're going to examine it for changes in the input. But the input, again, is not f of x, but we're going to input an f, or the input is not x, but f of a. And we're going to output, when we input f of a, we're going to output a corresponding g of f of a. And then instead of changing x by delta x like we did here, we were at x equals a, and then we added delta x to get to a new input. Now we're going to change our input. We're going to change our input, but remember, this is not just the x-axis. This is the f of x-axis. We're taking the outputs from f and making them the inputs to g of f of x. And so this change now is this change we saw right here. That delta f, which was f prime of a times delta x. So this is the change we're going to use down here. So just to kind of color code it, that change that we're going to make is that same delta f change we saw above. That was f prime of a times delta x. And that's going to give us to a new location. So what was f of a, we're now going to add f prime at a times delta x. Now that input of f of a plus f prime of a times delta x is going to produce an output. And that output, that vertical length, is going to be g of f of a plus f prime of a times delta x. Now I know it gets to be a little bit of a mouthful compared to up here where it was just a plus delta x. Now it's f of a plus f prime of a times delta x as we move over a horizontal distance, producing a new output, g of all of that. All right, now like before, we're looking for the rate of change. So as we change the input quantity by that amount of f prime of a delta x, we get a corresponding change in output. And just like up above, that change in output right here, that change in g is, let me do approximately, it's approximately that second output, this vertical length, which is this mouthful of g of f of a plus f prime of a times delta x minus the first input, or the first the first output quantity here of g of f of a. So we'll subtract g of f of a. Now, again, it's a mouthful, but it's the same patterning that we saw up here. F of a plus delta x minus f of a gives us that change in f right here. Now, it's g of f of a plus f prime of a times delta x minus g of f of a. Gives us at least an approximation for that change in g. Now, up here, we made a recognition that this is the numerator of our definition of derivative, f prime at a. So f prime at a. Now, likewise, this is the definition of the derivative, well, the numerator of the definition of derivative. This is the numerator, but not just f prime at a, but g prime at f of a. So playing the same role as f of a up here, that was that first input quantity, we now have g of f of a. F of a is that first input quantity. So it's g prime of f of a is the numerator there. But then like we did up here, you just have to imagine multiplying by delta x. So if we multiply by delta x, we get g prime of f of a times that change of x. But it's not just a change of x. Notice it's the change in that input quantity, f prime of a times delta x. So just like the delta x here, we now have f prime of a times delta x here. And so we say that the change in g can be approximated by this thing here. We have g prime of f of a, since we're composing an input of f of a now, times not just delta x, but the change in input is f prime of a times delta x. And we could manipulate this and say delta g delta x is approximately g prime of f of a times f prime at a. Now that was developed with a specific input quantity of a initially, but just know that we can now generalize this for any value of a, and we can say this: the derivative with respect to x of a composition of two functions. So in other words, changes in this composition of functions with respect to changes in x, changes in g with respect to changes in x, can be found as you see above. It's g prime of f of x times f prime at x. And there it is, the chain rule.